Good morning, everyone.
Good news, Professor Younger.
What's that? Good weather coming?
Yes, that, and I have all 20 observations for the Moon Project.
Right on. Good job. Kicking butt, Tyler.
Now, all I need to do is post the photos on Word document, convert it to PDF, and put it on Canvas.
Yeah, don't forget the details. The what direction, what phase, what date, what time. But you probably already got that set together.
Mm-hmm. Um, Question.
Yes, sir.
For my grades for astronomy. Hang on.
I've been meaning to talk to you about that. You got a zero. It's horrible. No, I'm just messing with you, buddy. What's up regarding
How
your
come
grades?
How come I'm still seeing missing for accommodation test 2 chapters 3 and 4 when I don't even have an accommodation?
Right. So the problem is, whenever I make one like that for a student that has to maybe take on a testing center, it appears in the grade book, and there's like it appears in everybody's grade book. So don't worry about it. If you've taken the tests one through, I guess it's five or six now. If you've taken each one of those, then you're golden.
It still says I'm missing for test 2 chapters 3 and 4. I already did that like
Is
last
there
week.
one showing a grade for test two?
There's one is showing a grade for test 2. The other says it's missing.
Then that's all that matters. As long as you've got one for test two, one for test one for test three, you're golden. Like I said, it just I don't know if there might be some smart way you can set up Canvas that it doesn't do that for the students that didn't take it, uh, but I haven't figured that out yet. So we just have to. The good thing is it's not counted in the grade, because what I do is when I make that, then I take that student's grade that they made and put it in the regular column, so that column's never counted as a grade. It might be instantly when I first make it, but then when I move the grade over, I go ahead and change it so it doesn't affect anyone.
Okay, hey, for the lab, the explorations and using the web, I already
Mhm.
turned it in for Thursday last week.
Right. If you see in that slot where it says the astro points thing where you turned it in, if you see that little, it puts something up there instead of a grade. As long as you see that's there, then you know you've turned it in and everything's golden. It's just a matter I'm waiting for everybody to turn it in before I grade it. It's hard to be consistent on your grading when some people don't turn it in at the exact same time as other people, so you always wait until the grade till you grade all of them. What I should do is really just grade them all on the due date, but then I have to be the ogre that presses everybody and gives them late points for our deductions for being late. And I try not to be that, at least during the quarantine. I know there's a lot of crap going on, and life is just a little more complicated than normal.
Yeah, you said when you posted for lab explorations and
Hmm.
web, it says 100 points for both of them on the dash. I see it on the dashboard for the canvas.
Hmm.
It says it's due by today, 11:59 p.m.
Yeah,
But
that was just me pushing it back in case, like, I had some people that actually had valid excuses, and if I put the due date to a certain date, then it'll show up to remind students, hey, it's getting ready to be due. So that's just me setting it back for those other students.
yeah, again, I already posted it last week, so
Yeah.
I'm good. I'm already good for
Tyler
that.
and everybody in general, do you guys know how to calculate a weighted average, like your grade, that the way college instructors make your grade usually? Because that's a big thing that everybody should know how to do. It's the way your GPA is calculated. It's the way most courses grade their students. Some courses just grade out of points, and they'll say, there's 842 points available this semester, and 90% of that is an A, and or stuff like that. People like to do that, but generally speaking, they'll say X percent is for tests, Y percent is for the midterm, Z percent for the final, Q% for the homework, and S% for the essays. Uh, do you know how to calculate an average? Anybody need some intro on how to do that in the event of such a grading system? That's something that everybody should know how to do. And that's really, I've never trusted an instructor's grade book. In fact, I never had access to them. But even when I asked an instructor if they knew how I was doing or if they just told me how I was doing, I always had a number to verify that they were wrong or right. And you guys should be doing that as well. You don't even have to do it by hand. You could just make it up in a spreadsheet and use it every time. But that's something you should know how to do. If y'all don't, make sure you ask me and I'll show you. I might even make a separate video and put it on YouTube so you guys can do it. Uh, I used to do that. I used to just give out a spreadsheet and a sheet for you to fill out about your astro points so you can keep up with it yourself. But like no one downloaded it, so that kind of made me a little aggravated. So I stopped doing it.
By the way, for the Astro Point the slot, the lecture and lab attendance, yeah, that should be a good grade.
Yeah, exactly. You should be very high. Like I don't think you haven't missed a day yet, have you?
No, not even close.
Yeah. So yeah, you can and I like to leave those until towards the end. Sometimes I'll put them in about mid semester just to let people know, hey, you're doing a lot better than you think because here's your astro points now that your attendance is there. But yeah, your astro points for attendance, lecture, and lab are huge. So yeah, that's a really good number of points that
By
you
the,
have already.
by the way, for the chapter 7 and 8 test,
Hmm.
Noticed that some of the questions that were on the test, those were the previous questions, like from chapters 3 and 4 and 1 and 2.
Exactly. That's what I mean by every test being comprehensive. And that's usually a result of if I see any students not making that 70 to 85% on some of the things I consider really critical for the course. So if students, for instance, can't do Kepler's third law at an 85% success rate, then I'll put Kepler's third law on the next test too. And if they
I
still can't do it, then I'll put it on the next test.
Just so you know, I am on a C streak for the test, but I can roll with that.
You cool with it? Well, I think you should shoot higher, but I'm glad that you're content with it. But I know you're a smart dude, so I know you could get a B if you try. So keep on pushing. And everybody do that. If I love to hear that students are happy, but I hate to hear them when they say, I'm content with a C. I get that. I mean, especially if you're not a science person, but always shoot for better. You'd be surprised how much you can do, especially in this class. I get a lot of students who are quote unquote bad science students and not good at science and not good at math. And they consistently get B's and A's in my class. So you guys can do it. Just don't sell yourself short. That's all I'm saying. Be
Okay,
happy. I'm awesome. I'm super happy that Tyler's content. But like I said, I know Tyler can do better than C. You guys know that he has really good subject questions. So
okay, that's all.
thank you, sir. Anybody else have any questions? Matthew, you got any?
I sort of do have a weird question.
Go ahead, John.
So when we normally have an eclipse, I know the moon is out during that time. So is it like when we have an eclipse, does the moon sort of like circle back again so we can have it at night, or is it just like a new moon?
No, it
Um,
only. Yeah, that's a key point. You can only have a solar eclipse during a new moon, and you can only have a lunar eclipse during a full moon.
oh, okay.
So yeah, there's no circling back. And the reason why it doesn't happen every time is, if you imagine whirling a ball over your head, you could whirl the ball such that it comes down and crosses your face, or you could whirl the ball so that it goes over your face, or you could whirl the ball so that it goes below your face. That's more or less what happens. The orbit is tilted with respect to the what we think is the orbit of the sun, but it's actually the orbit of the Earth. There's a tilt of about 6 degrees of the orbit of the moon. So unless we happen to be along one of these lines right here, we're not going to get an eclipse. But if we're along or very close to one of these lines right here, then we do get an eclipse during a full moon or a new moon, depending on which kind of eclipse you want. That was a good
Thank
question.
you. I was just thinking about it during spring break, and I just forgot to ask you that last week.
Yeah, and that's a lot how learning goes. You'll learn about it in your class, and then 3 or 4 weeks later, or sometimes the next semester, it'll hit you in the head, and you're like, "Oh, I get that now," because your brain sort of molds that and over and stuff from time to time. I think. I don't know that it does it subconsciously, but maybe it does, but I know that we do it somewhat consciously when we're just bored. We start thinking about stuff, and that's an excellent thing to do. Is keep some of these facts memorized and try to work out how they make sense. Really, the if you read the Science of Discworld, that series of books, they all talk about narrativium, which is like this made up thing about making a narrative. So if you have a narrative that make the facts all consistent with one another and seem to make cause and effect, then it's not about memory anymore. It's almost purely about understanding how things work, and therefore the answer just would never leave you. Why would it leave you? You just think it out again. Does that make sense, gentlemen?
Yes, sir.
That's a good series of books, by the way. I do not recommend you reading it unless you're really awesome, because the first time I read it, I had to quit like 3 times, and finally I listened to it on tape and then came back and read it, and I could. I mean, it's supposed to be entertaining, but it is tough reading. That man that wrote it, Terry Pritchett, I think his name is, or Hatchet, or no, I think that's the Wonder Woman chick, or Superman chick or something. Terry Hatcher's Superman chick. Anyways, yeah, it's like Terry Pritchett or something. He recently died in the last decade or so, and he had Alzheimer's. But he was a brilliant man, and he probably knew more about science than I do, even though he was, a literary figure. But he has a whole series called Discworld, the Science of Discworld, and it's all pretending like these are wizards, sort of like a Hogwarts type university, but it's a university, and they're on a flat Earth. At least as far as they're concerned, they're on a flat Earth, and they're sort of describe the whole history of the universe and everything. They even make a experiment that creates the universe. So I definitely recommend you guys checking that out. If you're really awesome and you can read well, which I couldn't, because I graduated from like third from last in a class of I think 60 at high school, and I'd only read 3 books when I graduated. I have been catching up on that ever since. So I'm not that strong of a reader and a very slow reader, and I'm improving, but that is hard reading. And even though it's entertaining, it's not about not being entertaining. It's about being funny. But holy crap, there's a thick, meaty sentences that you learn something every sentence just about. So, and it is on my list of books you can read, any of that series. But I think I put one up there. All right. Any other questions before we move on? Feel free to ask me about that calculating your grade stuff. That's something I really want all my students to do. I've taught my daughters how to do it. I've had cases. A good friend of mine, his daughter was failing a class, and he had worked out the grades of his daughter and knew they weren't failing, but they weren't great, but they weren't failing. So he finally had a meeting with the teacher where he discovered him and the teacher both, and the teacher, or excuse me, him and the principal and the teacher, but him and the principal both realized that what was going on is the teacher didn't know how to do a weighted average, and in fact was doing it wrong. Luckily, the principal was a math teacher, so he knew, as well as the friend of mine who was a science teacher, and basically the student was about to get an F in a course in their class, specifically because the teacher didn't know how to do properly calculate a grade. And no one would have caught that if it wouldn't have been for the student, and therefore, and also the parent calculating it. Now, you guys are grown up, so you're not supposed to have your parents necessarily calculating it, but if they know how, then get them to help you, and then you do it. But that happens a lot. I know a lot of people that don't teach math and don't teach science that don't know how to calculate weighted averages. So if they're using weighted averages, there's a high probability they might be leaning on their software so much that they might not be getting it right. So I definitely recommend you guys doing your own calculations. And don't be ashamed. Virtually every student I run into, other than I would say maybe 3 out of 24 know how to actually calculate their average. So if you don't feel bad. It's something you should feel bad about, in the sense that you should know that by now, but not feel bad about because you don't, because, like I said, you're small, you're part of a huge majority that doesn't know. All right. Well, it looks like I'm getting on my soapbox again, so I better stop that. Amy, I didn't get a reply to you from you regarding the question I asked about why you needed a second one. So if you send me an answer to that, we might still be able to set that up for you, and I'll take care of it and contact you via email. So just remember to read my email and get back with me on that. Uh, everybody else, I think I've been answering everybody's emails usually within 24 hours. So has anybody sent me an email that I missed? I don't think I have. So let me know if I have. That's one of the reasons I meet here. But the other reason, of course, is to cover material. And last time we covered chapter 10, which was on worlds of ice and water or something like that. And this one's going to be on basically the rings and the moons. So this is chapter 11. Let me look real quick at, I'm going to look real quick at our course and see what our last test was, just so, you know, I've got 5 courses going, so I never know what class is doing what, but I just want to double check so I don't accidentally say something incorrectly. It looks like the last practice test we did was test 4, which is on chapters 7 and 8. The next test, of course, should be on chapters 9 and 10. And that practice test is not up either. So what I'm probably going to do, since we've already finished chapter 10 last time, I'm probably going to make practice test 5, which covers chapter 9 and 10. I'm going to make them available probably today or tomorrow. And maybe Thursday, I'll go ahead and open it up and give you till Tuesday to get test 5 done. Okay. I don't know. I might just wait till Tuesday just because I usually like you to have a whole week with the practice test before. I mean, you sort of still do. If I put it up today, you'll have essentially a week, but I might push it off because it's not that big of a rush. If anybody has any ruthers on that, feel free to email your preferences as whether you'd like to have it open Thursday and be due on Tuesday, or whether you'd have it open Tuesday of next week and be due on Thursday, or maybe even Friday. Actually, if I do it Thursday, I'll keep it open until, or excuse me, if I open it Tuesday, I'll keep it open until Saturday night. So at least you have one weekend night. So if you have a preference, let me know. Otherwise, I'm just going to go with it and let you know when I decide. So today we're going to start chapter 11, and let me find that PowerPoint that I'm using for that chapter. And then I will read your learning goals because that's what good instructors do, and I'm pretending to be one today. So that's always fun when Mr. Younger pretends to be a good instructor. So, and again, your chapter sort of, I mean, your PowerPoint sort of show it, but here's the learning goals that we're shooting for here. I'm going to enable editing and I'm going to make it full screen, but the learning goals are, by the end of this chapter, you should be able to compare the orbits and formation of regular and irregular moons. Big hint, regular moons tend to have nearly circular orbits, and they lie in the equatorial plane or pretty close to the equatorial plane of the planet, and they rotate in, or I should say they revolve in the same direction as the planet rotates. That means they're more likely to have been part of the original disk of matter that formed from the planetesimal along with the planetesimal. The irregular ones tend to have more elliptical orbits, can be retrograde or prograde, not necessarily in the orbital plane with the equator, and they tend to be, of course, capture type planets. Or even collision type planets, but that's not always the case. For instance, the Earth's moon fits the regular orbit category, but it was in fact a collision with a planet we think of named Theia, and that happened, which happened to be about the size of Mars, and that happened about 4.3 billion years ago and made our moon. So that's not always the case. Learning goal 2 is describe the evidence for geological activity in liquid oceans on some of the moons. So we're looking for what evidence is there for active geological activity, which means there's internal heat inside of the moon. Learning goal 3 is describe the composition, origin, and general structure of the rings of the giant planets. And learning goal 4, explain the role gravity plays in the structure of the rings and the behavior of the ring particles. So we're going to see neat new gravitational things. Well, I shouldn't say new. They're sort of the same results we've seen in the past, but now they're actually acting on individual particle type things as opposed to full planets. So it's kind of interesting. I have resonance and cool stuff like that. So let's get cracking. So planetary moons and rings is the name of this chapter. And it opens up with a beautiful image from Cassini of Saturn. You can find a wonderful picture like this online, and I wish I knew the writer's name. There's a female writer who writes. I think she writes specifically for NASA, but she might write for some other groups as well, or instead of now. But she did this great analysis of this, and there's a picture. It looks almost exactly like this, but right here there's a little dot, and it's so cool because that little dot is Earth. I just think that picture is so cool. It's not unlike the picture pale blue dot that Carl Sagan wrote a whole book about. That it basically he talked for because there's no scientific reason to do it, but he talked NASA into taking Voyager on its way out of our solar system, turning it around and taking a photograph of the Earth from out, basically beyond Pluto. And he took that picture, and it was, sort of this monumental thing where it's the Copernican revolution coming home to us, realizing, every person we've ever met, every person we've ever read of, every person we think ever existed, everything that ever happened regarding our planet all happened in this little photo area. And it's just really impressive. And he managed to write a whole book out of it. And that book, I think, is probably better than most textbooks in describing our individual planets, even though it's now dated. So I would definitely check that out if you get a chance, or if you're interested in astronomy. What is the difference between regular and irregular moons? I gave you that already. Are all moons geologically dead? You can see this is going right along with the learning goals. Where do rings come from, other than spouses, boyfriends, girlfriends, whatnot? How does gravity affect the structure and behavior of rings? Those are all things like the learning goals. These are some really cool pictures of the moons. This one on the left is Phobos. That's actually the bigger moon from Mars. There's Phobos and Deimos. I'm probably doing a horrible job pronouncing them. Every time I see the word Phoebe, I just call it Phoebe, and I don't know if that's right or not. I just think of Friends. In the middle, that's the picture that I think looks most like the planet Hell. If Hell was a planet, that's exactly what it would look like. I mean, it looks all sulfury, reddy, bloody. It's just horrible. That's the moon Io, which is the second moon out from Jupiter and one of the 4 Galilean moons. And then to the right there is Enceladus, which is a awesome, beautiful moon with blue tiger stripes and basically a huge albedo. Notice it's almost completely white, so that means almost all the light it gets, it bounces right back. That's what the albedo is. There are dozens of worlds of rock and ice orbiting other worlds in our solar system, and some are large and some are small. Your book has a table that shows them all to scale, and you can see, for instance, that the moon is bigger than many, the moons are bigger than many of the planets. So, for instance, are at least bigger than Mercury. And for instance, some of the cases, our moon, which is not that big, it's about a quarter the size of our planet. Our moon is actually bigger than, for instance, Pluto, a planet. So there isn't always a size difference between a planet, a dwarf planet, and a moon. You can have moons bigger than dwarf planets, and you can have dwarf planets bigger than moons, and all that good stuff. The moons vary widely in their atmosphere and their volcanic activity. We actually have some that have volcanic activity in the traditional sense, with rock and magma and explosions of lava and stuff like that. And then we have ones that have volcanism that's due to ices, cryovolcanism is what they call it. And some moons have icy surfaces, whereas others have liquid water under their surfaces. We're actually going to, if you're reading the book, you'll see there's like 5 different moons that are likely to have a liquid ocean below an icy surface. That's kind of cool. That's something that makes those places now targets for future missions, because wherever there's water, just from a scientific standpoint, if we assume that the Copernican revolution is true and there's quote unquote nothing necessarily special about our part of the environment, and we've seen that life here required water, then we think if you have water, then you're likely to have life. That would be a wonderful contribution to the scientific literature and to scientific knowledge, is to find life on another planet, or find that there is no life on another planet, which is a lot harder to prove. There is no life is a lot harder to prove. In fact, it's impossible to prove if you just say all the planets. But in our solar system, you could sort of rule it out mostly, probably. But even then, there might be something on a smaller scale that we just haven't seen. But like I said, finding life on another planet would be very interesting. Would it have DNA? We think it has to have something like a DNA or an RNA type molecule. But would it be made entirely different? Would it have different amino acids that it uses? All sorts of stuff like that. Those are big questions. What if we were to discover that it had sort of some of the similarities with our DNA, or maybe it had an overlap with our DNA? Is that sort of the idea of panspermia, where some flying object hit a planet and delivered some biological material that was able to form life in that new place? There's all sorts of cool questions that come out of that if we discover it. So that's why we're, planning missions to Enceladus, for instance, and Europa. So yes, go ahead.
I have a question, and let me give some context to this question before anything, because I'm gonna sound insane. Okay? So, I play this game called Remnant from the Ashes. In the lore, there is a planet that is completely made out of organic material. The planet is a life form in itself. It is a living, breathing thing. Is it possible for there to ever be a planet-sized life form?
I would say, yeah, in that we found single creatures of a species that literally is acres large in terms of plant life. I know there's some tree, if you will, for want of a better word. It's more like a hedge or a shrub or some kind of nasty tanglement of weeds, like where a rabbit would hide. But I know that exists, and that's supposed to be one continuous plant, and that's over acres. I could see a scenario where something might get that big. I don't know if I would say it's a whole planet, but I certainly could see really huge life being a possibility. I mean, the dinosaurs being one case, obviously, but they're quite a bit smaller than what we're talking about here. But yeah, like I said, I have seen plants that are actually acres in size, a single plant literally that is an acre in size or more. So that being said, I could imagine a scenario where some symbiosis forms between the ground, which is sort of what plants do already with roots. They're part of the ground system, where they could form a symbiosis. I don't think they could do it with the entire planet. Like once you start getting into convection zones and cores of hot molten metal and rock or whatever it's made of, it's still going to be hot and possibly molten. I don't think that could ever be part of a life in a robust way, but it could sort of look like, I don't know, sort of like a local sun for a life form that happens to be the crust of a planet, maybe. So that would be what I have to say about that. But that's a kind of interesting thing to think about. So
yeah, because
certainly think about that bush that I talked about.
Yeah, because like in the lore of it, the planet is actually like a living, breathing thing. Like it's not made out of rock; it's made out of meat. Like it's an animal.
Star Trek did something like that once as well. They had a planet that was alive in some sense. So yeah, that's kind of a neat idea. It would be cool. But like I said, I would sort of think the inner parts aren't going to really be part of the life as much as maybe the energy source, if that could happen.
Yeah. I always found Lovecraftian concepts very, very amazing. I have his books too, Lovecraft.
Who's this? Oh, Lovecraft, yeah.
Yeah. Well,
yeah, I agree. Someone chatted that they wish we could be in actual class. I agree with that. And the summer's probably not going to happen, but I'm leaning towards it possibly happening in the fall at least. So at least my department's going to start doing it in the fall. Each of us department heads get to choose. So here's that table I was talking about. And this is what I was talking about. You can see clearly Titan is bigger than Earth's moon, but also clearly the moon is bigger than Pluto. In fact, Ganymede is bigger than Mercury. So you can see really there's the dividing line between moon and planet is not size. It's not radius. Okay. So this gives you some of the major moons. Obviously, these are the Galilean moons, and they're in the order of increasing orbital distance: Io, Europa, Ganymede, and Callista Flockhart. Then in terms of Saturn, there's Mimas, Enceladus, Tethys, Dione, Rhea, maybe, I don't know, Titan, and Iapetus. And then Uranus has Miranda, Ariel, Umbriel, Titania, and Oberon. And Neptune has Triton. And Pluto, poor little Pluto, actually, believe it or not, has 5 moons. Okay, 5 moons. And it and Charon, which is its largest moon, which is about half the size of it, are actually tidally locked simultaneously together. So they're like 2 dancers where they always face each other. So not only is the moon tidally locked to the mother planet or the mother dwarf planet, but the dwarf planet is actually tidally locked to the moon, so they always face each other. They're lobsters, as Phoebe would say. He's a lobster. Lobsters mate for life, according to Phoebe on Friends. So that's what we're talking about. They're lifelong loves. It's a sweet little romance. Anyways, I don't know why I can't progress forward on my slides. So these are the moons. Like I said, all of them have interesting stuff. Europa, we think, has an underground sea, an under ice sea, as probably does Enceladus. You'll find also that they think, like, I think it was Ganymede might have one. Uh, Titan might have one, even though Titan also is the moon with the thickest atmosphere. And in fact, it's the only moon with a thick atmosphere, and its atmosphere is actually thicker than the atmosphere of Earth. So that's a kind of impressive things. And it's the only moon that we've ever sent anything to. We've actually sent a lander there. It landed and took a photograph, even really cool stuff. We've got it mapped out pretty well. We know the geography of it. We know what the atmosphere is made of. We can explain the colors as we can with these other cases. All sorts of cool stuff. So the moons are made of rock, ice, or both. So some are rock, some are ice, some are mixtures. In this case, they say you're seeing an ice crust with a saline ocean under it. And then you have a ice mantle or a rock mantle, and then a iron core. That's not unlike what you expect. This actually looks to me like it's Ganymede that they're talking about, and that is consistent with me just telling you that I think Ganymede was one of the ones they said might have an under surface ocean. If I remember correctly, that one's on the order of 80 kilometers deep. When you start talking whole moons covered with 80 to, in a couple of cases, hundreds of kilometers deep oceans, you're talking more water in that than we have on the entire surface of planet Earth, because this is actually a deep volume over the whole surface, as opposed to just a fleeting volume over parts of the surface.
Professor Younger, when
Yes.
for moon formation, when it said some were formed by collisions, that was the question from chapters 7 and 8 as well. Some of the questions were from chapter 9 and 10 as well.
Yeah, that's because we've actually in the process of talking about formation of our solar system, we discussed some of the methods that would create moons. So it's not that we're testing you in chapter 7 on chapter 11 materials. It's that chapter 11's mentioning stuff that came from chapter 7. But yeah, that's exactly right. And that's the nature of science, is science and math. Have you noticed if you ever like miss a math class for like a week, you come back and it's like you can never catch up? Well, that's because everything you're going to do on day 1, you're probably still going to be doing on the last day of class in your most advanced class, even though day 1 was in your least advanced class. So they literally expect you to retain everything. And that's sort of what's going on with science, is as you learn things, we expect you to know that from there on out. So some were formed by accretion and differentiation. Some were formed by collisions, like Tyler was just talking about. And we know, for instance, from Darwin's grandson, he had done calculations of the orbit, and he showed that basically the orbit of the moon used to be a lot smaller. And in fact, last night I was watching Earth, the Making of a Planet. And they were talking about, in, I think it was 450 billion years. No, 400 billion years ago, the orbit of the moon was only 14,000 miles from the center of the Earth, where it's like 250,000 miles now. So that gives you some idea of how close it was. But that's what happens when you get a collision. You get a collision that could actually create something that's in a particular location, and then over time it degrades or something like that, and ends up being quite a far away. They have diverse properties. Like I said, some are icy, some are rocky, some are both icy and rocky, some have under undersurface oceans. Some are undersurface oceans of really, really salty water, sort of like the Dead Sea type salt, all sorts of cool stuff like that. Most of the large moons in the solar system are what we call regular moons. That's the large moons. About 2/3 of them are irregular. So if you just take the total number of moons, about 2/3 of them are irregular and about 1/3 of them are regular. But if you cut out and just look at the large moons tend to be regular moons. And that's because it's really hard to capture huge things. When we captured, quote unquote, captured the moon, we didn't really capture it as much as we got hit by something about the size of Mars, which is about half our diameter. And at that time, our diameter was probably quite a bit larger, maybe 1/3 larger or something like that. And it hit it and it shook off our outer parts. And that part made sort of a ring around it that slowly accreted into a moon. That's not exactly what I call a capture as much as I'd call a catastrophe that happened to give us some good luck. So that's the nature. When you have something really big, it's really hard to capture it because they, by necessity, have a very large velocity when they're out in free space. So if they're just flying by you, they're going to have a huge speed. And if they're coming close to you, they're getting sped up by your gravity. So they'll have a velocity close to the close to the escape velocity of the planet. So you can imagine something the size of, let's say, our moon, which is good, is a really huge moon for the inner planets and pretty good size for the outer planets. If you had something that big, but with the escape velocity of the Earth, you can imagine it's not going to be easy to capture that with gravity unless there's some kind of collision. Like I said, regular moons orbit near the planet's equatorial plane. There can be a little tilt, that sort of stuff, but it's generally pretty close to it. They are close to the planet and travel in nearly circular orbits. They formed from an accretion disk while the planet was forming. Again, this is sort of consistent with our moon, but not necessarily, depending on how late you consider the collision with Theia. They revolve in the same direction the planet rotates. Again, all of this is consistent with something accreting, like in that last line, in the same place with the planetesimal. Most are tidally locked to their planet. The moon is, for instance, just like Mercury's tidally locked to the sun, which is obviously not a moon scenario, but a lot of these are tidally locked. And examples of regular moons are Jupiter's Galilean moons, so Io, Europa, Ganymede, and Callista Flockhart. And then, of course, Saturn's moon, Triton, not Triton. That's a different moon. 2/3 of the moons in the solar system are irregular. That's what I was talking about. When you cut it out for mass, it's, much more regular. But when you just say all the moons, period, which literally, I think Saturn is in the order of 97, 98 moons now, and Jupiter has over 100. So, there's a lot more moons than the ones we're discussing here. But the properties are, for the irregular moons, they're more elliptical orbit. The orbit is more inclined. They usually have retrograde orbits. They're more distant. They're captured bodies that formed elsewhere in the solar system. Many are small, only a few kilometers across, and I think kilometers roughly the dividing line before they just call it debris. And the largest is Triton, the moon of Neptune. And what you're looking at here in this top picture, this little green circle is the orbits of the Galilean moons. In fact, that green one's like the outermost, so that's Callista, which I keep calling Callista Flockhart, being funny. But anyways, that's how small those orbits are compared to the irregular moons that orbit Jupiter. So that's pretty impressive for that. I think this right here should be a part of Enceladus, because I think I recognize that that orange peel type surface. I might be wrong. Someone can correct me on that. Actually, let me check my picture real quick. Nope. That's Triton, the one they were talking about. That seems odd. I can't believe they would actually put the name of the thing they're talking about right next to the photograph of the thing they were talking about. No, so that is Triton. I must have been. I'm actually trying to look at it now. Oh, okay. Yeah, that looks different than what I thought it did at first. All right, so here's that table again. The giant planets have several large moons, and many are as large as or larger than the Earth's moon. Some are geologically active, whereas others used to be geologically active. Remember, geological activity means there's internal heat that can cause things like plate tectonics, are volcanism. Okay, that's what we mean by geologically active. And it's basically an ability to erase, or it gives it the ability to erase new impact craters. So new surfaces of moons, or even planets for that matter, are indicative of geological activity. And what we found earlier when we were talking about the Earth and other planets in general, terrestrial planets, is that geologic activity lasts longer based on the radius. So the larger the radius, the longer it is to likely have heat, because it actually loses heat in proportion to the square of the radius, because it loses it through its surface, and the surface is like 4 pi squared, and it holds on to heat, or has heat, based on its volume, which is r cubed. So the length of time that it holds its heat is proportional to r cubed and inversely proportional to r squared. So r cubed over r squared just equals r. So a planet that's twice as large as another is twice as likely to have geological activity. That's the rule. And that's not just planets. That means for moons as well. So if you find a really small moon like Miranda here, and let's say Miranda here is about 1/10 of the size of Titan, then she's about 1/10 as likely to have geological activity as Titan is. We know Titan has activity, and we actually know that Miranda probably doesn't. And if it did, it would probably be for some other thing. For instance, Io, which you can see is not that huge. Of course, it's smaller than Mercury, and Mercury is geologically dead. So we'd expect it to be geologically dead. It turns out, oh no, it's not geologically dead in any sense of the word. Well, I shouldn't say geologically. It's iologically. IO, isn't that great? IO, like input output. Anyways, the surface markings, craters, and brighter dark areas reveal the geologic activity. The moon categories are active now, possibly active now, active in the past, and never active. Okay, so those, that just makes sense from a time standpoint. It's relevant whether it's active now or whether it might be, meaning there's some debate on whether it is. Was it active in the past, and was it never active? Never active is pretty a rare thing, I would think, because if it has any size other than a few kilometers, then it's going to have some radioactive isotopes in there that can provide some heat. But as you can tell, if you're talking kilometers, maybe you don't have much radioactivity, and even if you did, it would be so small compared to the overall size of the Jimmy Jank, then it's not going to happen. The Jimmy Jank's a word I made up, I think. I've never heard it before. I don't believe I said it, but anyways, I did. So internal heat is necessary for a moon to be geologically active. Io, for instance, is the most volcanically active place we've ever found in the universe, and it's certainly the most volcanically active place in our solar system. And by all means that we're used to in terms of the moon and the earth and stuff, this should not be geologically active because it's considerably smaller than our moon. It's considerably smaller. Actually, I think it's comparable in size to our moon, but it's considerably smaller than Mercury, both of which are geologically inactive. In other words, they basically don't have any heat left inside of them. But in order for this to be the most volcanically active, it must have an ample supply of heat. And it turns out there's a neat reason that it does, and it comes from tidal stretching. It's in a resonant orbit with the three of the other Galilean moons. So the innermost three Galilean moons, Io, Europa, and Ganymede, are in a 1-2-4 orbit. So what that means is Io will go around 1, 2, 3, 4 times every time that Europa goes. Ganymede goes around twice, 1, 2. So basically, every 4 orbits, Io, Europa, and Jupiter are all in a line. And then in that same period, Io, Ganymede, and Callisto has gone around exactly 1 time. So in every 1 orbit, Ganymede is actually in line with Europa and Io and Jupiter. Because of that, when they get like that, just like the Earth swells up on the tides swell up on the side closest to the moon and farthest from the moon, well, Io will swell up on the side closest to Ganymede and Callisto. Io, Ganymede, yeah, Callisto. And it will swell up on the opposite side as well, which is the Jupiter side. So that means the planet's actually being squished this way and stretched this way. And then later on, it'll be back to a sphere. So that doing like this, your author mentions, is just like taking, say, a paper clip, and you do this with it long enough time, it can literally get enough heat that it will burn you, like it can blister you. So that's what's going on with the material inside of Io. And when you calculate how much energy that would create, you find that's exactly the amount of energy it needs to be as volcanically active as it is. So that's why it's so volcanically active. It's from tidal stretching. It's from those quote unquote tidal forces. And remember, tidal forces mean forces of gravity that differ in magnitude at different locations on the object being affected. So the near side has a greater gravitational pull on it than the far side or than the middle or something like that. The planet is one source of internal heat, and basically, like I said, it comes from that stretching and stuff. But you can see here's a photograph, and in one photograph we just happen to be flying by, and lo and behold, we see a volcano erupting and another volcano erupting. So what are the odds that you just happen to fly by Earth and see a volcano erupting? Well, this is just a moon, and it's considerably smaller than the Earth, and we just found two just by going by it once. So that's a sort of big deal. You can see where it's done it a lot. We actually can identify the colors by basically what kind of elements are there and compounds are there. Io's most volcanically active object in the solar system. Its properties are slightly larger than our moon. It's hot from tidal stretching and compressing, basically. It has hundreds of vents and active volcanoes. It has vast lava flows. Volcanoes and volcanic craters cover the surface. It has no impact craters. Remember, impact craters are a sign of an old surface. I actually did a calculation one time, and I think it was a calculus-based physics class that suggested that Io gets completely resurfaced every 9 months. Based on the volcanic activity. So I don't know if that data was that true, but that's a ballpark figure that I wouldn't imagine a textbook author would give you unless it was ballpark. Silicate magma eruptions occur, bright carbon dioxide snow occurs. It's got mountains twice as tall as Mount Everest. Now remember, this thing is slightly bigger than our moon, which remember our moon is only a quarter of the diameter of our Earth. So this thing is, let's say, a little bit bigger than a quarter of our Earth and has mountains more than twice the height of Mount Everest. That's pretty impressive. That's not unlike Olympus Mons, which is considerably bigger than Mount Everest, and that's on Mars, which is less than or about half the size of the Earth. So that's some pretty impressive stuff about Io. Here's Europa. And this is a zoom in of one of the photographs of the surface. And I mean, nothing to me looks more like a big pile of ice that's been frozen and then broken and then frozen and then broken and then frozen and then broken and then frozen and broken than this does. This photo looks very much like ice to me, and that's what it is. Europa is also geologically active. We think it has an internal heat source that's actually keeping the water below the ice in a liquid state. The properties are slightly smaller than our moon. It's heated also from tidal stretching, but not as hot as Io. It's composed of ice and rock with an iron core. The surface contains few impact craters. Again, that's because the geological activity causes this ice surface to move around so much that it's constantly breaking up and reforming itself. The crust looks like broken slabs that have shifted in a random position. Subsurface salty ocean is what we think. We don't know. This one's kind of weird. We don't know if it's tens of kilometers or hundreds of kilometers thick the ice is. So the ice might be as thin as 9 to 10, 12 kilometers, but it also might be as thick as 100 to 200 kilometers. That's a problem because one of our missions was to go here, land, melt a hole or drill a hole through the ice down to the water, and then drop a vehicle, sort of a drone, a fully functional drone that drives itself, because there's no way we can drive it, but it just drives itself, and it's going to go around and explore under the sea. There's some videos from the Universe series season 1 that tells you about one of these missions and shows you one of them being tested. But it's some pretty cool onboard science equipment, so it can look for microbial life and stuff like that. That's really one of our plans, is to, go to an under ice sea and look for life. Obviously, we wouldn't be expecting some of the what was one of those weird named creatures that you see under the sea in prehistoric times, Anomalosaurus. We don't expect necessarily to see that. We don't expect complex life, but we might find bacteria or diatoms or stuff like that. It's has a weak variable magnetic field, and it has water geysers, which are not unlike volcanoes made of water. A lot of these subsurface oceans that we find are due to gravimetric measurements. So if we send something that orbits it, we can detect the changes in gravity that are consistent with a subsurface ocean. That's a lot of how we figure that out. Enceladus, there's those beautiful tiger stripes. If I remember correctly, these are the ones they call lobate scarps as well. Enceladus is potentially active. Its properties are that it's partially young surface. It experiences cryovolcanism. Again, this is volcanoes with basically due not to rock being in its molten state, but due to rock ice being in a molten state, if you will, so i.e. water. Radio or water ice, it would make water. Of course, these other ices, there's could be a methane ice and stuff like that, ammonia ice. All those could become liquids, and they, of course, are not water. They're ammonia or methane. Radioactive decay in the core and tidal heating may provide the energy. There's ridges, faults, and smooth plains on the surface. There's the ridges that we see. There's like a fault. There's craters. There's those blue tiger stripes. And there's a liquid ocean again under the ice. I think this one's on the order of tens of kilometers deep, not hundreds of kilometers like the other one. I'm saying the other one because I can't remember which one we were just talking about that had a subsurface ocean. So the geological activity of Titan. So here's an actual photograph from the surface of Titan. It's not often you get to see that. It looks a lot like the surface of Mars, which we're seeing a lot lately. Have you guys been noticing that, watching in the news and seeing some of the cool photos that are coming back from Mars? Anybody?
Not on my news channel. They don't talk about it at all. After they sent it, it was it. They didn't talk about it anymore.
Well, I will tell you, I know Facebook is for us old people, not you young people. But Facebook has this one dude who keeps posting these pictures, 3D photos and stuff from the surface of Mars. I would highly, highly, highly recommend you find that guy, which I'm trying to look for right now, and follow him just for those photos. Now, I did find out one of his photos someone said was faked, which makes me want to tell you to go poke him in the eye if you see him. But it might have been something where it was fake and he didn't realize it. So that makes me feel maybe a little bit better. But anyways, if I can't find it right now, I will find it and send you guys an email about it. He's got a sort of an Asian sounding name without being trying to sound prejudiced or anything. It was like a single syllabic last name. God, I can't find it. That makes me so mad. The last one he posted was so cool. It was a panoramic 360 view of the surface of Mars, and you see rock that looks here it is, Mars 360. Well, duh, that's a different guy altogether. So yeah, follow Mars 360, MARS 360. That was the one that has the panoramic picture of the rock, and the rock looks like perfect sedimentary rock, except it's all perfectly horizontal. And then you realize, wait a second, I shouldn't have that kind of rock that high unless Mars was once covered with deep oceans. So I think this is all the etching due to erosion as opposed to actual sedimentary rocks. So if that's the case, that's a pretty weird situation. I still haven't found the other guy that had posted so many cool pictures. He posted a nighttime photograph of the sky of Mars. That was also a three-dimensional picture. So check out Mars 360, MARS 360 on Facebook, again, the old people network. And if I find this other guy's name in the next couple of seconds, then I will tell you now. Otherwise, I'm going to just have to stop and tell you later via email and so far. I'm a prolific Facebook poster, so it could go 12 hours before I find the post that I'm talking about. So I have to give up eventually. have some great extra posts. But I don't friend my students, so don't friend me on Facebook until you're finished with my courses. If you're going to take possibly 2 or more, make sure you finish the last one before you do so. But what you do, you're welcome to. I just don't want to ever have students making personal decisions about things that their instructor told them. That's the main reason I don't want to do that. So, anyways, I don't see it rather quickly, so I'm going to stop, even though I can't now because the excitement of Facebook has drawn me in. So there's Enceladus. That's another site that we would love to go to. Obviously, that's one of the missions that we would hope to set up for Mars or the European Space Agency, or even I think Qatar now is it Qatar or is it what's that other country? It's not Kuwait. That's building all the cool cities and stuff like that. Anyways, that might be another area that's building a space agency. I remember it was like 90% women working in the control room, and they just launched something to space. So I thought this was a huge day for the Arab world, and I'm probably stepping on some toes by calling that the Arab world, but I'll just say I was in awe and happy about it. So Saturn's largest moon, Titan, is probably active. So here's the cool pictures. You can see the atmosphere. See how thick that is? You can barely make out the surface. Here's some surface details where we think it actually has lakes and bays, if you will, on the surface, as well as, if you look here, we got an organic rich atmosphere and surface, an outer shell, a global subsurface ocean. So notice that's a pretty thick, deep one, a high pressure ice shell, and then a hydrosilicate core. So this is basically like a glass type core. So it's bigger than Mercury. It's got a thick nitrogen rich atmosphere. It probably was mostly ammonia and methane, but a lot of the ammonia can be broken up. And when it's broken up, it leaves nitrogen. The orange atmosphere is due to basically hydrocarbons. So ethane, methane, ethanol is a derivative of ethane. So alcohols basically, and all those things that actually can make smog, like you see in Buffy the Vampire Slayer episodes, sadly, because it's all over LA. And every time you look in the background, it's just haze. It's kind of sad because it's such a pretty area. But the smog is what you see is the entirety of the atmosphere on Titan. It has liquid methane lakes. So yeah, these lakes are lakes, but they're so cold, so cold that it's actually liquid methane. So methane, which appears as basically a farty smelling gas on Earth, is cold enough for it to be a liquid and makes little lakes and riverbeds and stuff like that. It's nearly absent of impact craters, which means its surface is definitely being turned over and changed rapidly. The terrain is similar to Earth. It has heat from radioactive decay. It has potential cryovolcanism, which is the source of the fresh surface methane. Methane tends to run out, and methane, in order for you to maintain a methane percentage in an atmosphere, you normally have to have a source. So that's what they're talking about here. They suspect cryovolcanism is the source that's keeping the methane levels high. Your book talks about how methane levels dissipate normally. Liquid ocean under the ice crust, and it has a surface of icy rocks, and it has a water cycle like we have here on Earth, but it's not water because water would be in the solid form. It has a methane cycle. So that can sort of lead to the same type of things that we see on the surface there, specifically because it is this sort of water cycle, only the liquid happens to not be water, but liquid methane. Here's Triton, Neptune's moon. Yeah, I guess I was just misremembering, but that definitely looks like that orangey sort of stuff. These parts was confusing me. That didn't look like what I had thought. But anyways, this is Triton. It has a young surface, which shows that it's geologically active. Its terrain is like a cantaloupe. Yeah, that's the wording I remember. Cantaloupe skin, not orange. The skin shows geologic activity. It's an irregular moon. It has a retrograde orbit. It's got nitrogen geysers, methane and nitrogen ice surface, and it has volcanic plains. So there's little flat areas where lava flowed and made a flat area. Ganymede, you remember it's Io, Europa, Ganymede, and Callisto. So Io, Europa, Ganymede was the 3 moons I kept talking about. I think I might have been continuing to say Callisto, but I was meaning Ganymede when I was talking about the 3 in resonances. But Ganymede's example of a formerly active moon. You can see when they become active, basically they usually get a thick mantle This has an iron core, a rocky mantle, and then an ice mantle. So that's sort of making up the thickness, if you will. And then a saline ocean and an ice crust. It has impact scars that are filled, and they're actually quite bright, which is another neat surface. If you look at it, it does not look like something that's a bright surface, but from a light standpoint, it is quite bright. It's got a high albedo, despite having that darkish hue to it. Its heat source powers geological activity, and mostly from the early differentiation. So when it's in its molten state, the most dense things can fall to the core. That's why we have a iron core and rocky on the outside. And it's larger than Mercury. It has lots of impact craters, so it's got an ancient surface. It is fully differentiated. Remember, that just means different densities. The higher the density, or the deeper you go, the higher the density is. And bright terrain from unknown past tectonic processes. So in fact, you have cracks and stuff like that that could be like plate tectonics, but we're not really sure because they're not really exactly like we'd expect, seeing how our plates behave on the surface of the Earth. So that's kind of a confusing thing. Other formerly active moons. This is Mimas. And it's really weird in that it's a small moon and it has a crater on it about a third of its diameter. Basically, you're approaching the maximum size where something can get hit by and not be completely destroyed with this one. So this is really a potentially into the moon, hitting it, but it's kind of cool that we managed to hold on to the crater of this rather than it be completely destroyed. Other moons show signs of surface being formerly active, including bright and dark areas and tectonic fracturing. Examples are Dione and Mimas of Saturn. That's this Mimas that we're seeing here. Miranda and Ariel of Uranus. Yep. Callisto shows no sign of early geologic activity. It's got this cool area called Valhalla, which I like just because of the name. If I remember correctly, that's like another name for sort of heavens for the Amazons. So I'm picturing Xena warrior princess and the Amazons that she fought.
Wait, I thought it was for the Norse gods.
Yeah, that's what it is. Thank you for correcting me on that. Yeah, that's what Valhalla was. It was Norse. Thank you. I'm really bad at my mythology. The book I'm reading is not helping at all.
I just remembered Thor. That's how.
Yeah. I think Amy would have caught me on it too. Amy, did you get my email on that book I recommended? Don't mess with it. It's pretty raunchy once you get to some of the mythologies towards the end. So, anyways, it's the book I told her about.
I got your email.
Okay. Yeah, the book I told her about was called Zeus Grants Dumb Wishes. And it's a book that someone used for mythology class at TCC at one time. That's how I found out about it. And it's funny. I mean, it's hilarious the way he wrote it, but it gets really raunchy, which, all the mythologies are raunchy, but this guy takes it to the next level. So anyways, Callisto's properties are its dark, heavily cratered surface. It has bright regions where subsurface ice has been exposed after impact. And other geologically dead moons include Umbriel of Uranus. I noticed I said it in a mature way. And Hyperion of Saturn. Check out Hyperion, man. Isn't that some creepy looking stuff right there? It definitely looks like a loofah. Like I could totally pumice my corns with that.
Why is it considered dead?
A dead just means no longer has an internal heat source capable of making volcanism, tectonism, and that sort of thing.
Oh.
Yeah.
Okay, I get what you're trying to say now.
Yeah, they're just saying it's not going to change. So anything that happens to it's going to stay now. This one, on the other hand, I don't even know. Like I said, it does look like a loofah. Basically, they expect it to have a ton of canyons and all sorts of cool stuff. The ring systems. One of the big things you got to understand about the ring systems is they're a product of the time period. If we come back 12 million years from now, we might not have a Saturn with rings. Maybe it takes longer than 12 million. If we come back, say, 1 billion years, it certainly will not have rings. Other is lucky in that it has a source, a few different sources that can keep it maintaining its rings. The other Jovian planets have rings, but they're a lot less prominent, and that's because they don't have some of the things that can restore the rings. So the ring systems are around all the giant planets, only around the giant planets. There's none of them on the small planets. They consist of small orbiting particles they're usually larger in diameter compared to their radius than a pancake. So they're way, way thinner than they are wide. The faint rings were discovered by stellar occultation, meaning in one case, like we were just flying by Jupiter and we saw the light from the sun in the background go tinkle, tinkle, twinkle. And that little twinkle, twinkle, twinkle turned out to be the rings of Jupiter. And if it wouldn't have been for that, we wouldn't have known the rings, Jupiter had rings. Later, we found out that, in fact, all the Jovian planets have rings. Saturn rings are the largest and brightest, and they just are really awesome to look at. That would be a really cool thing we could do if I could get you guys to come up to the observatory at like 2 in the morning. Actually, I think it's more like 4 in the morning, 5 in the morning. We could actually catch Saturn and Jupiter just before the sun rises, but that's about all you can do right now is catch them that early in the day. They're not up at night, in other words. So the ring systems look like this. Here's Jupiter. You got the radius of Jupiter. You have the halo, and then it has only a main section, a gossamer inner ring, and then a gossamer outer ring. And gossamers, if you know that from poetry, it just means really, really thin or faint. Saturn, on the other hand, it has the A ring, which actually is just inside of the F ring. Then it has the Cassini division, because Cassini, I think, was the guy that discovered that, among other things. Then it has the B ring, and then the C ring, and then the D ring of the innermost. But then we say, oh, wow, there's an E ring way the crap out here, and there's even an F ring just outside of A, and then there's a G ring outside of F, but inside of E. So we labeled them A, B, C, D as we were going along, but we didn't discover them in the right order necessarily. So that's why they're in that weird order. They have a Triton ringlet, a Maxwell ringlet, an Inky gap, a Keeler gap. We find things called satellite, or excuse me, shepherd moons, where you'll see literally a moon riding along inside of the rings, pulling along another ring, and you'll even see little waves in the, or I say pulling along another moon, not a ring, pulling along another moon, and then you'll see the ring in between the two moons actually forming like a wave that rides right along the gravitational pull right in between the two moons. Cool stuff like that are seen all the time in Saturn's rings. It's just really cool to look at. If you look at Neptune's rings, you can see here's the radius of, or excuse me, Uranus rings. I didn't mean Neptune. Here's the radius of Uranus is way out here. This is going out to this area. And then you see out here, you got rings 4, 5, and 6, which are the innermost rings. Then alpha, beta, eta, gamma. So obviously eta they found after gamma, and then delta, lambda, epsilon. So it's got a lot of very thin rings in the case of Uranus. In the case of Neptune, it has actually thick rings, but fewer in number. So it has the Galli, I'm not sure how to pronounce that, Leverrier, the Lassell, the Arago, the unnamed, and the Adams ring. So these rings, like I said, are just small particles of rock and dust and ice and stuff like that. And they're held gravitationally, obviously, in orbit. And we find resonances, just like we found resonances with Io, Europa, and Ganymede. We find resonances with things within the rings as well. And that can cause things like gaps and inky gaps and stuff like the inky gap and stuff like that. Ring particles, of course, follow Kepler's laws. That's kind of neat because we can actually get a spectra of a planet. And we've talked about this before, but if you get the spectra, say, of Saturn, I have some photographs of the spectra of Saturn that I used to use for a lab. I still would like to use it for a lab, but it really needs hands-on stuff. But you'll see the lines of the spectra on one side shifted this way and the other side shifted that way. That's because the planet's rotating. So one side is red shifted because it's going away from you, and the other side is blue shifted because it's coming towards you. And the same thing happens with the individual rings. The lines on the rings will actually shift as well. And you can see as you get further out in the rings, the Doppler shift changes, completely consistent with Kepler's third law, meaning, remember, Kepler's third law is the square of the period is proportional to the cube of the semi-major axis. Man, one of my students can draw on the actual thing. Anyways, so that no, that's okay. I didn't know it could do it. So that actually gives a velocity distance relationship, and the velocity relationship we get is exactly consistent with Kepler's third law. The vertical motions cancel out, leaving the particles moving in a plane. The larger moons can affect the orbits. Moons can pull particles slowly toward them, causing a low density gap. And shepherd moons can herd ring particles into narrow rings. I think they'll have a, no, they didn't have a photo. I was really hoping to have a photo of that. You can check them out. Just do a Google search for shepherd moons, and you'll see some pictures. The material found in the planetary rings is probably a result of tidal stresses. The gravitational force is stronger on the side of an object closest to a planet than on the more distant side. The Roche limit is the point at which tidal stresses are greater than the self-gravity of a body. So a moon or planetesimal that comes within the Roche limit is pulled apart into little pieces. The little pieces, of course, form the rings. The pieces spread out, orbits circularize and flatten, and the pieces are distributed around the planet in form of a ring. How did you actually write that for future reference? Because that's something that could be helpful for my students.
In the bottom left-hand corner, there's like a little pen icon, and I clicked it, and it just gives you the option to highlight or draw. And I thought like, oh, cool, it'll just pop up on my screen. And then I'm like, oh no, everybody saw that.
That's cool. I don't mind at all that you discovered something. So that'll help me. If you guys have questions, y'all can point out like that. And I assume there's even a way you can erase it. It doesn't appear to be on the actual slide, so it's not a big deal, but definitely make use of that when y'all have questions. The ring composition is the same as the composition of the moons they come from. So Saturn's rings are bright and are mostly water ice. Uranus and Neptune's rings are dark and mostly radiation darkened organic materials and ices. Remember, it's sort of like snow. When you get snow on your car or snow on the ground, as the end of the winter season approaches, if you're living in Michigan or somewhere cold like that, the snow starts to look quite black and ugly and sooty. That's sort of what happens to anything white in space too. It's going to pick up carbon and all the other stuff that's out in space. That's what they're talking about with Uranus and Neptune's rings are dark and mostly radiation darkened organic materials. The radiation can actually burn off and cause different compounds to form, and that causes a blackening as well. Jupiter's rings are intermediate brightness and are rich in silicates, like the inner moons. Again, you can see the moons are actually feeding the rings. And moons can contribute material through volcanism. That's the easiest way. Of course, there's other ways as well, just from impacts and whatnot. Saturn's rings were first seen by Galileo in 1610, but not recognized as rings for a long time. In fact, it wasn't until Maxwell, I think, died in 1855, 1835, somewhere around that era. But he was the one that actually showed that they couldn't be solid objects. They couldn't be ears or whatever that Galileo called them. He showed that they had to be individual particles. Huygens in 1655 used a better telescope and recognized them as rings. Saturn rings are a very complicated system composed of thousands of ringlets, each made up of tiny orbiting particles that obey Kepler's laws. They are bright and dark rings. There's gaps and there's divisions. The gaps are not empty. They actually have stuff in them, but they're usually darker and just way less dense. Brightness or darkness reflect the amount of material in each ring. Though wide, the ring system is extremely thin. If Saturn rings were as thick as a piece of paper, the rings would be 6 football fields wide. So you can imagine the ratio is a sheet of paper to 6 football fields. So yeah, that's a pretty darn thin thing. Even though some of these rocks are literally stories tall, so we're talking, tens of at least multiple meters, tens of meters, maybe on the order of several tens of meters in size are the rocks. Diffuse rings are fader and have no defined boundaries. This is also like that photo that I told you about where I saw the Earth in. There's Phoebe there, there's Titan there, Iapetus here. And you can see Saturn inside. Saturn's largest ring is a diffuse dust ring discovered in 2009. The E and G ring are also diffuse. So ones that don't have clear boundaries are just called diffuse. I think that makes some sense. Here's the shepherd moons. Okay, see the little wave I was talking about? So Prometheus and Pandora, they're sort of gravitationally interacting with each other, and they can pull little particles to get along. So there could be a particle right here in this gap, and it'd be being pulled along by Prometheus. But also you can see the gravity actually affecting the actual rings in between the two things. So this is Prometheus and Pandora. The rings are kept stable by shepherd moons, and shepherd moons can also distort rings.
1045.
Thank you, sir. Thank you. Gravity can cause distortions, including what looks like twists and waves. Other distortions include scallop shapes and appearance of transient spokes. So you can see the little scallop shape right here. Spokes grow in radial direction and last for less than half an orbit around Saturn, indicating that particles in the spokes must be suspended above the ring plane, probably by electrostatic forces. The rings of other giant planets are mostly narrow and diffuse. Backlighting brings them into view, like that cat up there. And Neptune has denser sections known as ring arcs. You can see one there. Rings do not last forever. Collisions in sunlight destroy the rings, and shepherd moons can help stabilize them, and orbital resonances can create gaps. And we are done. So, yes, we're done. You folks are free to go, of course, but I'm here to ask the very last question that anybody has, assuming it doesn't interfere with my next class that starts in a few minutes. But thank you for coming, everybody. We had now finished chapter 11, and I will make the practice test available hopefully today.
Okay. Have a very nice day, sir.
Do you see you, Matthew?
I have a question.
Yes, ma'am.
It's about the exploration lab. That's for your lab class, right? And if they wanted to get extra points?
Yeah, so the way it is in my lab class, you get it as a lab. You too, Amy. You get credit for it as a lab, so I'll grade it as a lab, and that's part of your lab grade. But if you're in my lecture, you also get it as astro points, so you can do it as astro points, and you might even be able to convince your teacher, if you have another one for lab, they might be able to give you points for it, but I doubt it since it's the lab side. If it was the other way around, it might be useful. But you can do it as well, just to get the astro points if you'd like.
Okay, so how do I complete it then?
Basically, it's the explorations from chapter. Anybody remember? Was it chapter 9 or chapter 10? I think it says it. If you click on it, it'll tell you what it's about. But there's an exploration at the end of the chapter, and if you actually, and the same thing with the using the web part, that's when you can do. I want to say it was chapter 9. Yeah, it was chapter 9. Chapter 9 exploration, which was called climate change. And it has basically, you read something and you answer 7 questions, talk about experiments and stuff like that. So if you do that, writing out all the questions or copying them as necessary, and then answering them in a different color font, saving it as a Word document with your name in the file name, and then saving the final result once you've added any pictures, drawings, anything you needed added to it, then save it as a Word document, and then save it as a PDF and turn that in. Far as the other one goes, the using the web, you were entitled to do 40, any question 46 through 50 you were allowed to do. I really wanted people to do 49, but you could do any one of them you wanted, and that would count for 200 astro points, and the explorations counted for 100 astro points. So that was what the assignment was.
And that was on chapter 9, the 46 through
50, as well as the explorations that came right after it.
Okay, thank you. I appreciate it.
You're welcome. See you, Leanna.
Bye-bye.
Amanda, you have a question, or Jamie?
No, I don't.
Okay, we'll have a good one. And like I said, I'll be making the next test, which covers chapters 9 and 10. I'll be making a practice test available for that soon. And the actual test will either be put out Thursday or Tuesday of next week. You folks have a good day. Jamie, you don't have any questions, right? I don't think he's here. Have a good one.